if anyone needs an exam, there will be an exam for those who need the exam. I mean, we don't have the exam, let's say, as a for everybody. If anyone doesn't need, there's no need to take an exam. But if you are enrolled in any PhD school and for that you need to have to obtain credits for the course, we can, of course, we will our PhD office will issue a letter with the duration of the course. And in some PhD schools, to have credits, you also need to show a kind of pass. So for those who need this, just let us know. We have a simple test in the end, which normally has been applying this simple code that is the MATLAB code that let's say allows to do the basic calculation of the linear stability analysis to a river context of your choice. So it could be your field site for your research, some river you are interested in, the river that flows close to your house, and your laboratory flume if you're doing experiments. I mean, just whatever type of fluvial context you would like to analyze, and just to test what it means in that context to apply and just comment the results basically. But I can be more specific tomorrow with presenting a written, let's say, assignment. It will be a home assignment that you can do once the course is finished, and just maybe Marco's arrived. Okay. Ciao.
Here it is.
Marco Colombini.
Some Marco Colombini with some focaccia. This is one of the focaccia.
Don't be sure what we can have now or later.
You can have whatever. Just okay. You just started.
We're just speaking about the exam and so.
Okay. We have to decide a little about the change of plan because I
yeah. But
read just now
I can stop at 3.
Okay.
And they can have a break.
Sure.
Can be
Eat
focaccia. We can discuss.
Sure. Okay.
Okay.
So we will see
Okay.
you here at the.
Yeah, so we'll wait for the focaccia.
Okay. But if one is able not to steal some of it without him, it's okay. Right.
Excuse me.
Yes.
The examination could be, for example, providing a report or something.
Yeah. So you do the calculation and then you write a short report on the calculation. You don't necessarily have to use that MATLAB code if you don't have any access to any lists. You can do a code by yourself, but it takes more time. We also have a web-based tool, but it's very recent, so I just tried once. It's Python-based, but I cannot say 100% it works perfectly. So, but if anyone is interested, I just need to check, and we can provide this thing. Not sure how it's working because we did it last year a bit for fun, and then we didn't close the thing. But it's Emilio, as always. Okay. So one thing. So please just let me know who needs to do a final needs or would like to do a final assignment, just to put in practice the concepts of the course. Okay. In the last day, we will ask you to fill a simple evaluation sheet before leaving. On what you think about the course, what could be improved, what was good, expectations, met, not met, and so on. Last but not least, on Thursday night we plan to have a dinner, a joint dinner of the course. So it would be good if some of you can help in just knowing how many people are coming, so then the next days we can make a reservation. Roughly about 8 in town. So don't have a budget. We didn't ask you to pay anything for the course, but we cannot pay. So everyone will pay for the year. Yeah, okay. So that's basically side information. What I will do in this bit less than an hour is to move from the questionnaires that you have filled. And so I had a look at the scores, and the scores at the answers. And the first ones are mostly blue, are mostly yes. 1/3 of the participants say that they do not know what the second derivative of a function is, so maybe it's an issue of terminology, but I will explain. Maybe you know actually, but I was expressing not very well. But then there is half of the people saying, I don't know what the shallow water equation for hydrodynamics are, and also the external sediment continuity equation is, so I will review these concepts now, just briefly. So some of you will be very basic if you have done a course in hydraulics or in fluid hydraulics, but if not, this can be new concepts. I do not pretend you will fully understand what they are if you never heard of them, but just to frame them a bit. And how to calculate. 1/4 says it does not really know what the normal flow and how to calculate the normal flow with the Chezy law. Maybe you know it is in another way. Let's see. So, most of you or all of you said that you know that if you have a function of one variable, let's say f, as a function of x, this is the graph, this is how we indicate. The first derivative is expressed in this way. This is the first derivative. And it basically expresses the rate of change, how much, let's say in a point, the function changes if you change the x variable. So for a given, I will be quite approximate, not really mathematically precise. So for a given dx, how much will be the variation of f? So the derivative will be positive if the function is increasing, it will be negative if the function is decreasing, and so on. And the derivative is also a function in itself. Then if you do the derivative of the derivative, you have the second derivative. That's what I meant with the second derivative. So the derivative of the first derivative is just the second derivative, which normally has the 2 here, because it's second derivative of the function f with respect to the independent variable x 2 times. First and second. That's what I was meaning. Maybe you all know. All the mathematical equations that we will solve to look for equilibrium, the perturbation, and so on are differential equations. So it means that they are formulated with respect to derivatives. So it's very important that we are sure we understand the basic concepts of derivatives. And the second derivative is normally, well, graphically you can see that the second derivative, you can remember in this way, it is negative when the function is below the tangent, and it is positive when the function is above the tangent locally, more or less. It means that well, when the first derivative, here the first derivative is negative because the function is decreasing, and here the after this saddle point, the first derivative is positive. So first derivative is negative, then it is positive. It means that the derivative of the derivative will be positive because the first derivative will pass from negative to positive. Just to remember. We will have some second derivatives in the equations, though we do not see them. When we write the equation, we will not see any second derivative, but when we add the relation for settlement transport, and especially for bed forms and for bars, the relation that expresses the effect of gravity on the direction of the bed of transport, this will add a second derivative of the bed elevation function. And this term will be very important because it's a very strong stabilizing effect. So we will see that the equations, you can view equations as the sum or the composition of different terms, different mathematical terms. Every mathematical terms will have a role. It's like a player. Will have a role towards stability or instability. And typically that term, which is very important, is the fact how gravity acts on the particle that is moving on the bed. And this is of course stabilizing, because you can imagine that if a particle is here, gravity will somehow tend to push the particle in the trough, and so to fill the perturbation and not so gravity somehow stabilizing, and this will come out in a term that has the second derivative of the bed. This said, shallow water equation. I write the form of the shallow water equation that I was, so I'll just erase this. Shallow water equation. I'll take it from the very far. When we study a physical problem, at least a mechanical problem, like in fluid mechanics, so to study the motion of a fluid, we have general conservation laws that are normally the conservation of momentum and the conservation of mass. I'm sure that you have heard of this, at least when studying basic physics of a rigid body. If you apply this conservation principle, momentum conservation means force equal to mass times acceleration for a rigid body that is moving. If you apply this to a fluid that is moving, a fluid doesn't have its own shape, it adapts to the container. It has some type of relation between the speed of deformation and the shear stresses, the forces inside the fluid and so on, and turbulent behavior or whatever. Then you get some type of equation, which are the most complex, the Navier-Stokes equations, which are a three-dimensional model. You can theoretically describe every type of motion of every type of fluid. To study bars and to study bed forms, what is normally used are, let's say, simplified forms of the Navier-Stokes equation, which are way too complex, way too detailed to study this process. So, in the study of bars, for example, we use a 2D model. 2D model means equations. 2D equations that average shallow water. These are also called the 2D Summerer model or equation. So I'll write them and then we can try to read them. Let's start with the momentum conservation. It's not important that you remember all the terms, but it's important that I think when you have an equation, you are able to read behind the symbol. So, some basic terminology. This terminology here is a derivative, but it's a partial derivative, because here we have functions like u or v. These are the two components of the velocity vector, the flow velocity. Let's list the functions. Which we also call dependent variables. We have the flow velocity. Our domain is what I draw for spatial references what we saw this morning. So straight channel in the xy plane, and x and y sorry, are the horizontal coordinates. So x is trimwise and y is lateral across the section. Then we have water surface elevation. H, and water depth or flow depth, which is capital D. These are our unknowns. This is, we would like to solve those equations to know what's the value, the behavior of how these functions, so how the velocity, the depth, and the water surface elevation change in this space, and also in time. Here I didn't put time, but time will appear in another equation. Actually, this is the, well, we will, to be more complete, we can put the time term, temporal derivative, but this will not be, will be neglected in the analytical derivative. But then we have the independent variables, so our coordinates. We have x and y, the spatial coordinates, and time, the temporal coordinate. Gamma is the specific weight of the fluid. G is gravity acceleration. And I realized that if I put G here, sorry, this is not gamma, but this is rho. And so this becomes simply water density. And this is gravity acceleration. Tau x and tau y are also unknowns, and are is the near bed shear stress. That has two components, tau x and tau y. So to visualize, you can imagine in whatever point, here we have, if you measure the velocity, the velocity vector will be something like this, with a longitudinal component and a lateral component. There will be some value of the depth and some value of the water surface elevation. I can use this diagram. So H will be measured from the same reference level we use for every elevation, is the quantity H, while the depth is the difference between the water surface elevation and the riverbed elevation. So there is a relation between H and D that gives the bed elevation. Eta, that we defined this morning as the riverbed elevation, the morphology, the elevation of the riverbed, is the difference between the water surface elevation and the depth. Okay? The three variables are linked to one another. What do these, so you can view, just to connect with what they mean, this part in yellow is the acceleration term, is the acceleration of the fluid. It has a local component and a advective component. So, but it's, if you think about force equal to mass time acceleration, this is the acceleration of the fluid in time and in space. This is the so-called Lagrangian acceleration, if you have done some course in hydraulics. And then we have the external forces. Here they are condensed in two terms, but we have the weight, gravity, basically the gravity effect. Here we also have pressure, force, and here we have friction. We have basically the friction between the fluid and the boundary through the shear stresses that are the forces per unit area that the fluid acts on the riverbed, on the boundary. And these are the forces that actually tend to mobilize the sediment, so it's very important. These equations, you will see during the derivation, are not solved exactly from this form because the shear stress actually depends on the flow velocity and on the depth. So we don't have so many unknowns. The actual number of unknowns in the analytical theory will be 4 unknowns, which can be U, V, H, and D. Any combination of these unknowns can be used, but we will come back to this later on. So, acceleration. Here we have, these terms are gravity, so weight and pressure. And these terms are quantified friction. So the red and the green part are, hope they're not colored right. These two parts are the external forces acting, surface forces and volume forces. And this is the acceleration part. Navier-Stokes also express the same balance, but in a much more detailed way. This model is two-dimensional because the spatial independent variable are two. We have two directional space. Navier-Stokes is a 3D model. When you will study, you will see, starting this afternoon with Marco Colombini, one-dimensional bend forms, you will start from a 1D model from this. So one equation only, and only one spatial variable x. But the approach and the method will be essentially the same. The stability analysis will be the same, but they are that average because all quantities are, I simply draw an aerial view. So we don't have any information of how these quantities change on the water column. Okay. It's just a depth average. They're called shallow water because to obtain these, some steps behind, there's the assumption that the horizontal scale at which we have variation of the flow are much longer than the vertical scales on which we have variations. And this yields quite a famous group of equations, especially for fluid mechanicists and applied mathematicians, that are called shallow water equations. There are mathematicians that work maybe only on those type of equations. Because mathematically they have a specific nature and a specific methods to be solved. I don't think you need much more to know if you never had heard about them. At least to know what they mean, basically. For 1D bed forms, you will start from a further momentum conservation equation that is the average is obtained from them by averaging over the lateral direction. It becomes one dimension because you even rule out the lateral coordinate, you only keep the longitudinal coordinate. Some questions, clarifications? Okay. The system of equation from which we will start for the bars also has two more equations that express the conservation of mass. I will go directly to the conservation of mass for the sediments, which is called the extra sediment continuity equation, because it was one of the answers that has most no in the answer. Can I erase? But now everything is recorded. Okay, the excellent sediment continuity equation is, I would say, is the fundamental equation of morphodynamics, which can be, takes a very simple form, is a continuity equation. We'll see, so it relates mathematically a temporal derivative of a state variable with a spatial derivative of a flux variable. Now we will exemplify it quite in a simple way. It can be used at very different spatial and temporal scale for all the possible morphodynamics applications that I was suggesting this morning, not only rivers, but geological time scales, ice, lava flows, and so on. Let's take now, I will propose a 1D version, just to explain what it is, because it's simpler. Let's take a side view. We have our riverbed. I will take a control volume, just an idealized volume in our flow. We have our water surface. We have the bed elevation eta here. We take a control volume which has a length delta x. And let's suppose we know how much sediment enters into the control volume, QB in, and let's suppose to know, we also know how much sediment flows out of the control volume, QB out. So QB is the sediment rate, the sediment discharge. So is the volume of sediments per unit time that enters into the control volume, QB in, and the QB out is the volume of sediment per unit time that goes out of the control volume. This is also a unit, let's say, per unit time and per unit width, because we are taking a kind of a strip. We're not considering the width, it's one. So, just think very intuitively. If, like these two arrows suggest, if we have less sediment entering here compared to the amount of sediment that is going out, do you expect the riverbed here to lower or to go higher? To lower. So we expect to have erosion. Erosion means that eta will decrease in time. Okay? So we are saying that if, well, let's write it here, if QB in is smaller than QB out, then we have that eta will decrease in time, which we call erosion. This is in very intuitive terms. And the other way around, if we have more sediments entering than what is coming out, we expect the riverbed elevation to lift up and to have deposition. If we write now in mathematical terms, it means that in this case, less sediment entering, more sediment going out. It means that, so this is case 1. In case 1, the derivative of QB in the x is positive. And we also said that in this case, eta will decrease in time, so the time derivative of eta will be negative. So there is the two derivatives, one in space of the sediment flux, one in time of the state variable, which is the bed elevation, have an opposite sign, and vice versa. This is the main principle. So in the 1D case, it's very simple. So scouring is not because there is a lot of sediment transport. Scouring is because sediment transport is increasing in the downstream direction. Deposition, from this continuity principle, is because sediment transport is decreasing in the downstream direction. So the Exner, the 1D model, writes in this way. This is the 1D version of the Exner equation, where P is an important variable that we often neglect. It's important, but P is the porosity of the sediments. Because the difference in height of at which the bed elevation will increase or decrease will depend, of course, on the volume that is deposited here. But these fluxes are, let's say, volume fluxes, but the actual volume also needs to come from the pore spaces between the sediments that are set. So this equation will be coupled with the momentum equation for the water, where we will see that the shear stresses will be used to calculate the sediment flux. And that's how they are connected. Actually, you will discuss with Nunzio on Friday that they are connected also because if eta changes, then the slope will change in the flow equations. The flow equations has that it was not explicit in the formulation I wrote, but in the term that has derivative of h in the x, which is the slope of the water surface, there's also the river bed slope. So the change in the bed elevation will affect, in general, will affect the slope that affects the flow, and the flow creates a different shear stress, which affect the sediment flux, which affect the bed elevation. So the problem is coupled. It means we have to solve all these equations in principle simultaneously. Then you will see with Marco, starting this afternoon, that in some cases it is possible to assume that these effects can be decoupled, so you can, in some situation, you can solve the flow and then solve the river bed. Also, when computing, when doing numerical simulation, that's all the issue of morphological factor to accelerate the simulation and so on. We can discuss with Nunzio these things when it's reasonable, when it can pose some risks. Questions? Yes.
Is there any equation that we can calculate the number of the particles?
Sorry?
Is there any equation that we can calculate the number of the sediment in each value?
The number, you mean the number of particles?
Yeah, which is
You mean SPA, like SPH technique, smooth particle hydrodynamics?
like stochastic equation that.
Yeah, I know there are studies on that. There are simulations. I know there are direct Navier-Stokes simulations where you simulate the motion of. You input a certain number of particles and you just follow every particle. I know there is some limitation so far with the Reynolds number on the flow you can simulate, but of course, computer power will increase. For fluvial application, it's not so standard yet, but
You want to ask how to calculate the QB, the
okay.
sediment transport rate.
Okay, yeah, okay.
Aced and,
Yeah, so we need to, maybe I erase here. So that's a good point, and it relates with the last out in the end. So the last question about the normal flow and the Chezy law. So I said before, from the momentum equation, we have tau x, tau y. They can be expressed as function of the flow velocity, the net. The basic, and this is one closure relation. We have equation, and then you need some semi-empirical relation to close. This is in the 1D case. For example, we have tau x equal to density, longitudinal velocity at the second power, dimensionless Chezy coefficient at the second power. This C, there's always someone who is used the dimensional and the dimensionless, but with this I'm meaning so if I use the Strickler coefficient, this would be common Strickler relation is something like this, where Ks is Gauss-Strickler coefficient, or if you're more used to Manning, then this will be N is the Manning coefficient. This is just somehow an empirical formula or semi-empirical formula. This C is called dimensionless Chesy coefficient. And now I come to your question. So this is one closure relation we need with the first two equations. With this equation, we need a relation that allows to calculate the QB. There are many predictors of sediment transport. We know that the uncertainties are very high. Ask Walter what he thinks about sediment transport predictors. Not he thinks, but what is his belief. They are the, let's say, the best relation we can use, but there is a famous paper from Mike Church, who is a famous fluid geomorphologist, who wrote something like, based on the analysis of, I don't know how many sediment transport formula that were tested against field data, we can say that no sediment transport formula can reliably predict what we observe in the field, because the phenomenon is so complex that it's difficult to quantify the actual rate. But on a more positive side, we will see that one thing is to predict the amount of sediment that will be transported by a specific river in a specific flood. Another thing is to understand if I'm increasing the discharge or if I'm decreasing the weight, if I'm changing the control parameters, how the system will react. So these predictors are performing a bit better in that respect. One simple example. I will keep it quite fast, but so QB is the sediment discharge divided by the width of the channel, to be dimensionally consistent here. So this is a square meters per second, not cubic meters per second, lowercase q, because it's this is cubic meters per second and divided by the width. So what is normally used, there is a scale represented by the sides of the particle, G, then which symbol to use? We can use delta. This is what is called the Einstein scale. Gravity acceleration, sediment diameter, and this is density of sediments minus density of water divided by density of water. So it's the relative density of the sediments once it's wet, it's in water. This is gravity acceleration, times some dimensionless function, which we call phi, of a parameter that is called the Shields mobility parameter. So many predictors of the bedload rate in gravel bed rivers have a structure like this. This is when the sediment transport occurs mainly as a bed load which means that the particles are transported almost in continuous contact with the riverbed. When we have a suspended load, so fine material that basically is kept floating by the water, there are also some types of predictors of this type, but you need actually to add one differential equation. If we work with bed load, we can keep this. This is our power laws, more or less. Usually, a typical expression for phi is phi equal to a coefficient times theta minus a critical threshold value to a power that is 1.5 then. But there are tens of predictors that have been calibrated in different fluids, in different rivers. Everyone who does experiments in the lab says every fluid has its own bed load predictor. We have to derive the actual bed load predictor of this fluid, and I will use this because I know there is some of you doing experiments here, so I think you know what I mean. If you run numerical models like basement, Telemark, Delta-D, Hydro, AS, Mike, whatever you use, you probably run in the possibility to choose different bed load predictors, different coefficients, and usually these are calibration parameters against some data that you observe, so you run the simulations and you check if, for example, the areas that are supposed to transport sediments actually match with the observed ones, or depending on which type of data you can calculate. Well, the story will be much longer, but just to give an idea. So basically, the starting point for the bar theory are the momentum equation, so before, the mass continuity equation for water, which I didn't comment, but we can go if you want, and the sediment continuity equation, plus two types of what are called closure relations. So some relation that allows to establish a semi-empirical relation between the near bed shear stress and the flow velocity, which are needed in the flow equations, and between the sediment transport rates and the shear stress, essentially, of the flow field. In this way, the unknowns of those equations will be formed. But we will go back to them, to this, the next part. Did I answer? We have other questions? Maybe Marco is coming. So there is one question that is left over, which is calculation of normal flow using the Chesy law. Once we start with the bar, I will start. I will recap this. It's quite simple. It basically comes from here, and assuming that all the spatial and temporal derivatives are zero in the equations, so the equation becomes very simple from how complex they look now. Okay.